Sure. So 22 is probably the trickiest one here algebraically. So it reads that two toy racetracks form concentric circles. So I'm going to start by just kind of drawing myself a picture. When we say concentric circles, we mean that like one circle is inside of the other. So something like this. It says each racetrack is divided into 15 identical sections. So I'm just going to kind of draw one of those identical sections. Thank you. So let's label some parts there for those. So I have an R1 for the radius of that inner circle, S1 for the arc length there. I have an R2 and an S2 and then a theta. So far so good? What? We're okay? Okay. So I'm just drawing the picture of concentric circles and labeling some parts here. It says if the inside car travels 1.2 centimeters less than the outer car on each piece of track, so that tells me that S1 is S2 minus 1.2. It says how much bigger is the radius of the outside track compared to the inside track. Set up two equations using the arc length formula and use substitution to solve. Okay, well, I guess I'll just do this, and I'm going to plan on finding my angle in degrees, so I'm just going to use that version. So far, so good. Haven't really done much. Okay. So the first thing I can do is I can find a value for theta. So since I know that there's 360 degrees kind of in this circle and we're dividing it up into 15 sections, theta should be 24 degrees. Just 360 divided by 15. So I'm going to plop that in there. I'm just going to write that as a fraction as 24 pi over 180 rather than two separate pieces, just because it is a little bit neater to do that way. And I know I could reduce that, but this is not my final answer involving, so I'm just going to throw it in there and take care of it later on the calculator or whatever. And now if I look here, it looks like I have two equations, right? But I have 1, 2, 3, 4 unknowns. I know from last year's algebra course, if I have 4 unknowns and I want to solve that system, I better have 4 equations. So it doesn't appear that I have enough information as I've currently constructed this problem, right? Here's the catch. Does the question actually ask for the values of R1 and R2? No, it's asking for the difference between R1 and R2, right? So that's actually what I'm going to worry about trying to solve for is R2 minus R1. So I'm going to go and I'm going to take equation 2 and I'm going to subtract from it equation 1. When I do that on the left-hand side, I have S2 minus S1. Then I have R2 times 24 pi over 180 minus R1 times 24 pi over 180. Okay with my substitution I've made there? I notice that on the right-hand side that each of those have a 24 pi over 180, so I'm going to factor that out. And now I'm going to also make the observation here that S2 minus S1, well, I know what that is, right? I can take this equation And if I add 1.2 to both sides and subtract S1 from both sides, I know that S2 minus S1 is 1.2. So now I'm just going to multiply both sides by 180 over 24 pi, and there's my answer. I have to be a little bit careful when I'm doing this. So 1.2 times 180 over, and I got to make sure I do the 24 pi in a parenthesis in the denominator, or else it's going to divide by 24 and then multiply by pi after, rather than dividing by 24 pi, so you have to be a little bit careful there. That's going to give me about 286. I think this was in, what was the unit on this problem? Inches or something, I think? Centimeters. So algebraically, that was tough, right? To come up with, to realize that, hey, I can just solve for R2 minus R1, that I'm not going to solve for R1 and R2 separately, and I'm not going to be able to solve for S1 and S2, that I'm just going to have to worry about the difference there. That's sneaky, right? That's not an easy realization to make. Alternatively, what you could do is, what if we just pick a value for S1, say like S1 is 1. That means S2 has to be 1.2 bigger, has to be 2.2. I know theta in each of these cases has to be 24. And then I can solve for R1 and R2 individually and find the difference. You could do that too. Now that's maybe even less obvious why I can just fix a value for S1 and S2. But according to the description, it doesn't matter how big S1 and S2 is, it just matters what the difference is. And now I'm going to find a specific R1 and R2, but their difference should still be the 286 that I observed algebraically. So that's maybe the simpler way of going about it algebraically, but that required a big leap in going, oh, I can just fix a value for S1 and S2 and then grind this out to get my R1s and R2s and then subtract them. You avoid a lot of nasty algebra there, but maybe it's not entirely clear geometrically if it's okay to do that, right? But either route would get you the right answer. And just FYI, this is beyond what I'd expect you to be able to do on a test or a quiz. This is quite difficult algebraically. You had to make several difficult like algebraic assumptions and kind of solve a system in a way that maybe we're not entirely used to solving, right? Like instead of solving for a specific variable, we solve for this quantity of variables, this difference of R1 and R2. That's tough. That's tough. To come up with that on your own, having never seen that before, that would be tough. Just to be clear, right? Anthony, are you happy? Yeah, so we hammered that one pretty good, right? With a couple of different ways of going about doing that, but nice tools to put in your old mathematical toolbox there. Sydney, are you dying to ask a question right now?
I know, I'm just ready.
Okay, go for it.
So it's not like a question on the homework, it's just a general question.
Yeah, good, I love conceptual.
With the angles of rotation,
yeah.
if you had like 370, would you just draw like a swirl and then have like the line and right the little 10 degrees?
Right, so our standard form angle if we're doing 370. So the initial side is the positive x-axis. And then to find the terminal side, we're going to rotate around. So 90, 180, 270, 360, and 10 more puts me over here. And that's all.
Oh, okay. So you would rather do a little like 10 degrees?
You could if you wanted to,
Okay.
but I don't need you to do that.
Okay.
And obviously this is probably not very to scale, really. If it's 10 degrees, it should be like down here or whatever. But I'm not gonna be too picky if as long as you got it mostly in the right quadrant, you know. As close as you can be, reasonably, would be best, but I'm not gonna lose my stuff because it's like, oh, that's, you know, way more than 10 degrees. That looks more like 35 degrees. Like, I'm not gonna go that crazy. If you have it like more than halfway, I'll go crazy about that, but, you know. Jacob. 21? Sure. It says a pizza shop. Worker decides to cut a round pizza into 10 slices. Okay, let's start by drawing a picture. It says 10 equal slices. So again, I'm not going to draw all 10 of them, but since they're equal, I'm just going to draw one. So let's label some parts. I have R1, S1, theta. And since they're 10 equal slices, just like we mentioned on 22, I can find the value for theta really quickly by just taking 360 and dividing it by the number of slices. It says if the diameter of the pizza is 18, that means the radius is 9. So what is the length of each piece of crust? Well, that's the arc length, right? So I can just say that S is equal to R times theta. And since that's in degrees, I know I have to tack on the pi over 180. And then I just grind that through my calculator. Cool with that? Okay. Anthony.
Could you also do 18 pi divided by 10?
18 pi divided by 10. 18 pi. Yeah, I think that works out. So that's the whole circumference, and you divide it into 10 slices. Is that kind of what your thought was?
Yeah.
Yeah, I think that gives us the same answer. Let's just double check on the calculator. So 18 pi, pi divided by 10. Okay, yep, that's the same number, I think. I've done this several times today. Yaparuski. Tommy.
Can you do 24, please?
Yeah. So 24 is one of these unit conversion problems.
Yeah.
It's pretty similar to the example bike problem that I gave in the notes. So it says a circular saw has a diameter of 8.25 inches. And we know that there are 12 teeth per inch. On the cutting blade. And it says if the saw spins at 3,500 RPMs, how many teeth cross the surface each second? So I want to take RPMs and basically convert that into teeth per second. So I'm going to, again, note the same thing that we mentioned in the lectures, that one revolution is equal to one circumference. So in this case, that's going to be 8.25 pi inches. Good with that? Okay. So I'm going to start with 3,500 revolutions per 1 minute. I guess first thing I'll do is convert the time, so I know that there's 1 minute is 60 seconds, and I had to set up that ratio. I know minutes has to be on top so that they're diagonal and seconds on bottom. And then I'm going to worry about converting revolutions. I'm going to go revolutions to inches using the fact that I know 1 revolution is 1 circumference. And I'm going to go inches to teeth, knowing that there's 12 teeth per 1 inch. And then I'm just going to grind that through my calculator, because if I check my units here, just make sure I have this. Minutes canceled, inches canceled, revolutions canceled, and I should be left with teeth per second. So that should match the right unit. So 3,500 times 8.25 pi times 12. I'm just doing the whole numerator at once. Divides by, and then the denominator just really has the 60, so I don't even really need a parenthesis down there. If you have lots of things, though, you should put a parenthesis around the denominator. That gives me 18,143-ish. I don't think this one I was specific about where to round. But that's all she wrote there. Shorter even than the bike one that we did in the example. A few less conversion factors needed, but a little unfamiliar circumstance. But really we approached it the same way, right? Just as like a big unit conversion. And all the ratios that we needed were either given to us in the problem or were kind of, things that we could come up reasonably on our own. But again, the key there with any of these things that are spinning that involve RPMs is remembering that 1 revolution is 1 circumference. That's kind of usually the stumbling block. So again, I have one of my backgrounds is in chemistry, so I tend to want to set up all these unit conversion problems like you would in your chemistry class, right? Where you're just like converting moles to particles or something. You're like, oh my God, this again? Paul. 33, you say? Sure. So 33 says evaluate with, find the exact value without using your calculator. Okay. So at this point, if we're looking for an exact value without a calculator, we're going to need to use either the 30, 60, 90 or 45, 45, 90 triangles. So I remember from my geometry class that these are the ratios for the 30, 60, 90 and 45, 45, 90 triangles. This is something that'll come up again here for the next couple of chapters. Not a bad thing to have written down and perhaps even committed to memory. You'll use it fairly frequently here. So the question for me becomes, okay, we have cosecant of pi over 3. Is pi over 3 a 30, a 60, or a 45 degree angle? Well, I mean, I know, but if you're not sure, let's just do the conversion to degrees. So pi over 3 is 60 degrees, just multiplying by 180 over pi. So I'm going to be using the 60 degree angle. Cosecant, I remember, is the reciprocal of sine. Sine was opposite over hypotenuse. So cosecant is going to be hypotenuse over opposite. the x's reduce out of there. And then we rationalize our denominator. And I have 2 root 3 over 3. Paul, are you okay with what we did there? You don't sound very reassuring.
It's just a lot of steps. I think I got it.
Okay. I mean, we can go through something again if I buzz through something too fast.
Can we do like one of these?
Sure.
It's just like when we go down a calculator.
Yeah,
We do like 30.
sure. So 31 is sine of pi over 6. So again, I'm not going to redraw the triangles over here because I have them just above. I'm just going to use that again. So I'm just going to first start by converting pi over 6 into degrees, right? So just like you did in the first, 10 or so questions. So that's sine of 30. So I'm going to look at the 30-degree angle. I remember that sine is opposite over hypotenuse. So that's x over 2x, which reduces down to 1/2. And I'm done.
That makes
Yeah, you picked the most complicated one as your first example. Sydney?
I guess for the last one, where'd you get the x times the square root of 8?
So looking at the 60-degree angle, cosecant of 60 is the reciprocal of sine, so it's hypotenuse over opposite. The hypotenuse was 2x, and the side opposite the 60 is x root 3. So that's where the x root 3 comes from, is because it's the side opposite the 60. Is that okay?
Yeah. I just couldn't.
Gotcha. That's again, I know my penmanship is sometimes less than spectacular. If you have trouble reading something, like, you can stop me and be like, I can't read this thing or that thing, and I'll go back and write a little bit more clearly. That's important, right? It's hard to understand it if you can't read it. Jacob.
Number 39.
Sure. So on 39 it says for the requested variable, or solve for the requested variable based on the given information, round your answer to 2 decimal places. I'm just going to draw in the given information and just exclude all the other labels if that's okay with everybody, just to make the picture a little less, with stuff going on. So I'm looking to solve for this side C. I'm going to use the angle I know. Relative to the angle I know, the side I know is the adjacent, and the side I'm looking for is the hypotenuse. So I need to select the trig function involving adjacent and hypotenuse. I would pick cosine. So I'll say cosine of 38 equals adjacent over hypotenuse. And now I'm just going to solve this equation for C. So I'll start by multiplying both sides by C to get it out of the denominator. Remember again that cosine of 38 is just like some crummy decimal. Thank you. So I can just treat it like a decimal here and divide both sides by cosine 38. Now, realistically, you could convert cosine 38 into a decimal just using your calculator or whatever. I wouldn't do that until the very end because every time you do an arithmetic, you're going to have to do some rounding, and then you potentially create a lot of error, enough error that like you could get the wrong answer. But I'm just going to hang on to the cosine 38 until I'm ready to go to my calculator, which is where I'm ready to do now, since the c is all by itself. So I'll turn my calculator on. Whenever I'm going to use sine, cosine, or tangent, I'm going to check the mode of my calculator to make sure that I'm in the correct mode. Since this problem, we're doing cosine of 38 degrees. I'm going to check my calculator to make sure I'm in degree mode. So I press the mode button. If you're not in degree mode, you just use your arrows to move down onto the degree and press enter. That'll make the degree highlighted and unhighlight at the same time the radian. So you do need to double check that. Then I can just type in 10 divided by cosine 38. And I get 12.69. And just to kind of ask myself, does that make sense? The side I'm finding is the hypotenuse, so it should be bigger than the other sides that I know, which it is in this case, which is usually a pretty good sign that I'm on the right track. Does that feel okay, Jacob? Okay. Again, this was all stuff that we should have done 2 years ago in your geometry course. Somebody pointed out to me earlier today that, like, yeah, 2 years ago, like this time in geometry, we were learning online at home. So like that might be we might not have done a great job with that. So again, if it feels like I'm blazing through something, acting like you should know what's going on, and you're like, this seems really foggy and I'm not really sure what's going on, please stop me and remind me that, like, hey, this might have been one of those parts like that we just started not have it all the way, and I can stop and we can fill in some of those blanks. So like in particular, when we're dealing with like solving these little right triangles and stuff, this is something that you would have ideally done a lot of in your geometry course that maybe we didn't do that much of because of the circumstances of 2 years ago, which again is something that like I didn't really think about until somebody reminded me this morning. So I've kind of blazed through some of that stuff that maybe isn't a great idea that I did that. So again, if we need to take a day and kind of rehash some of those ideas or part of a day, we can do that. So just giving you guys the heads up on that to just let me know if we get to a spot where it's like, this is like a blank. Like, I don't know what you think that I'm supposed to remember from this, but I don't know it. And we can go back and try to fill that stuff in. Okay? And that's my bad for not thinking about that until somebody pointed it out to me. But, you know, we'll be doing it for a couple of years where the people are, you know, where we had that missing semester or whatever. Maddie.
Can you tell me 25, please?
Sure. So 25, I'm just going to draw the picture here and put the labels on and then do that. Okay with you, Maddie?
Yeah.
3, 4, 5. So in this it says, find the value of all 6 trigonometric functions for the angle theta in the triangle based on the given measurements. Leave your answers exact. So the 6 are going to be sine theta, cosine theta, tangent theta, and we'll have cosecant theta, secant theta, and then cotangent theta. Okay. So relative to the theta, yeah.
Can you do that equation? There's no right.
Oh, sorry. There's a right triangle in the picture. I just forgot to draw it. Thank you, Sydney. Very good. Anyway, so let's start with sine. Relative to the angle theta, opposite over hypotenuse is sine. The opposite in this case is the 3. And the hypotenuse is the 5, so just have 3 over 5. Relative to the theta, cosine is adjacent over hypotenuse. The adjacent side is 4. The hypotenuse is 5. Tangent is opposite over adjacent, so 3 over 4. Cosecant is the reciprocal of sine, so I can write 5/3, or I could think about it as hypotenuse over opposite. That's fine also. Secant is the reciprocal of cosine, so 5/4, or you could think about it as hypotenuse over adjacent. And cotangent is the reciprocal of tangent, so 4/3, or you could think about it as adjacent over opposite. My suggestion to you is to remember them as reciprocals rather than like hypotenuse over adjacent or something, because that information is going to move forward and be valuable. We're going to abandon side lengths of triangles in terms of how we're calculating these sine, cosine, and tangents here in another section or two. So those aren't going to be great to hold on to, but the reciprocal relationship is really valuable, and that will continue to be valuable all the way to the end. My suggestion to you on how you remember which one are reciprocal pairs, obviously tangent, cotangent, it's easy to remember because they both have tangent in them. To remember whether sine and cosecant or secant and cos, which ones go together, I just know that no cos go together. So cosine and cosecant don't go together. Cosine goes with secant and sine goes with cosecant. So just to help you kind of remember that, that's typically going to be the easiest way to remember and kind of the most valuable moving forward. Sydney.
Right, with the abbreviation for the reciprocal of cosine, is that SEC?
Yes.
Okay.
Yes. Yeah. So it's short for secant, which again, if you remember from geometry, a secant, what was that? It was like it's like a line like this that goes through a circle. That was a piece of geometry vocab. Again, that would have been a second semester thing that maybe we didn't do a great job with. As opposed to like a tangent that hits the circle in just one point instead of 2 points. I don't know. Again, this is me realizing that we have some geometry gaps and just trying to, as it comes up and, in the flow of a conversation, just kind of fill in some of those little, little vocab, but it's reusing that word. Okay. Who's next? Maddie, you're happy with what we did there, though?
Yeah.
Okay. Jacob. 44? Okay. So it says find the values of two different angles coterminal with the given angle. One of your answers must be positive and one of them must be negative. So before we do this, just let's review what we mean by coterminal. Because of all the things we've talked about so far conceptually, like these ideas in section 2-3 are the ones that kind of move forward with us the most and are kind of the most important moving forward. So in section 2-3, we describe a new way to kind of define an angle. We say, okay, we're going to embed an angle in the xy axis where the vertex is at the origin. One arm of the angle we're going to fix on the positive side of the x-axis. We're going to call that the initial side. And the other arm we're going to allow to rotate counterclockwise for a positive angle and clockwise for a negative angle, however many degrees until we get to the end. So for example, if I'm doing like 120 degrees, well, I go like 90 degrees to here, and then like 30 more would put me over to here, right? Now, we call this side the terminal side. So any angle, any other angle, whose terminal side is in the same location, we would say is coterminal to this. So for example, if I go around one full time and then back to here, that would be an angle that's coterminal, right? So we did one full rotation, that's 360 degrees, and then did the 120. So that's like a 480 degree angle. And a 120 degree angle are coterminal because the terminal sides are in the exact same location. Does that feel okay with what we mean by just the vocabulary sense? Sydney?
So you're saying that it like ends in the same place that like, so let's say your terminal, if it ends in the same place as terminal, coterminal?
Yes, they're coterminal, as in their terminal sides are the exact same spot. They're like collinears, two lines that overlap each other. Coterminal is the two terminal sides overlap each
So
other.
if it was like 125, it wouldn't be coterminal?
Correct. Yes. So the big takeaway from what we've just seen here is basically if I do add multiples of 360, that'll get me another coterminal angle, right? 120 plus 360 was 480. If I added another 360 to 480, that would also be coterminal. Or if I added another 360 to that, it would be coterminal because 360 is just going around and then ending up right at the starting place again, right? So that's the takeaway. So to get my coterminal angles, I'm just going to be adding or subtracting 360 degrees. Now, I notice that in 44, this angle that we're given is in radians. So instead of adding 360 degrees, I'm going to be adding 2 pi, because that's the radian equivalent to 360 degrees. So to add 2 pi over 7 plus 2 pi, I need to make a common denominator. Should be clear that common denominator would be 7. So I have 2 pi over 7 plus 14 pi over 7, which gives me 16 pi over 7. I guess, by the way, I knew that since 2 pi over 7 is positive, and I'm adding 2 pi to it, I'm going to get a positive angle back from this. The directions ask for one positive angle and one negative one, so I knew that I'd have to add to get the positive one. To get the negative angle, instead of adding, I'm going to be subtracting. So I'm just going to do the same thing, 2 pi over 7, but this time I'm going to subtract 2 pi. I'll make my common denominator. And that gives me negative 12 pi over 7. So there's a negative angle. What would I do if, for example, I subtracted 2 pi and I didn't get a negative? I would just subtract 2 pi again. And if I didn't get a negative there, just keep subtracting and 2 pi's until it come out to be something negative. Sydney.
If it's like a larger number, can you subtract like, let's say you have subtracting 2 pi, would you subtract 12 pi off the bat, like you know that's going to cause a negative?
Yeah, you could subtract a multiple of 2 pi right away. So like 6 times 2 pi, sure. Also, just FYI, if you don't want to deal with the fractions on your calculator, for example, instead of doing 2 pi over 7 plus 2 pi by hand, I can just do 2/7 plus 2 on my calculator and then use the fraction command. And it'll give me the fraction just to, to save some pencil lead from having to grind through adding fractions, which is sometimes just kind of a pain. Sydney?
So this would be your answer, you don't need to like put it into decimal form?
Correct. This would be fine. Yep. Alexis?
If you had to find another coterminal, would you just subtract another 2 pi over 7 to like the negative 12 pi over 7?
Yeah, so if I needed another coterminal, I could either add 2 pi again to 12 or 16 over 7, or I could subtract another 2 pi from 12 pi over 7. Either would be fine. They both give you another coterminal. And you could do that in perpetuity. You can have infinitely many coterminal angles. So as you can keep generating them as long as you want. You're never going to run out of coterminals. Does this feel okay? The big takeaway for me is that you're able to draw the standard position angle. That becomes really the super valuable skill going forward, is that you're able to draw like a 570-degree angle and end up in the correct quadrant. So just kind of keep that in mind as we move forward. That'll be valuable. Sydney?
So if we're ever doing an equation like this, we always have a line across the x-axis and the initial plot on the initial line.
Yes, the initial is always on the positive x-axis.
Okay.
That's what standard form, that's part of the definition. Is that the vertex is at the origin and the initial side is on the positive x-axis.
Okay. So it's never going to be above or below.
Not for a standard form angle. There's other ways of describing angles that have a different definition that would do things a little bit differently, but we'll cross that bridge when we come to it.
Okay.
So when we talk about standard form angle, we're talking about this way of drawing it.
Okay.
We'll talk about bearings a little bit later, which measure or start at a little bit different location. So, but we'll deal with that later. That's much later. Maddie!
Can you number 43 too?
Sure. 43 is easy now. Well, we've done all the hard part, building out the foundation here. So I have a 187-degree angle. To get a positive thing coterminal, I'll just add 360. To get my negative, I'll just subtract 360. No, it's easy. It's as easy as you want it to be. So that's it. That's not bad. Heck of a lot easier when it's in degrees, right? The arithmetic is easier anyways. Or feels more familiar.
Wait,
Yeah.
just a general question for this.
Yeah.
When you're doing like the s is equal to r times theta, you always want theta to be in radians when you do that, right?
So you can have we have two different versions of that formula. So there's s equals r theta, that's the radians version.
Got it.
Or if you tack on the conversion factor at the end, that'll work if theta's in degrees.
Okay.
So it's the same formula, I've just tacked on the conversion from degrees to radians to the end of it.
So either way, you're gonna have to translate into.
Yeah, whether you want to do it separately or do it as part of the formula, it doesn't really matter.
Okay. Thank you.
Yeah, no problem. Anthony,
Could you put another problem similar to that?
to the coterminal thing?
Yeah.
Sure. Tell me your favorite angle measure. 420. Oh, what a jokester. Okay? So this is a good one, though. So if I want a positive angle coterminal to this, surely I can add 360 to it, right? If I want a negative angle, if I subtract 360, I don't get a negative. What do? I just subtract it again.
So you can just keep subtracting until you need to.
Until you get what you're looking for, what you want, yeah.
So is this the same thing like what Cindy said? If you wanted to do like 12 pi right off the bat, you know it's gonna be too small.
Yeah.
You do the same thing.
Yeah, that's right. So just to kind of illustrate what's going on, 420 degrees, 90, 180, 270, 360, and like 60 more is there, right? 780 is 90, 180, 270, 360. Jeez, 540, 630, 720, oh, I'm sorry, 720, and then 60 more. And then negative 300, negative 90, negative 180, negative 270, and 30 more. Okay. So what I'm doing, so my initial side is here, and I'm going to be rotating 420 degrees, counterclockwise because it's positive. So each quadrant is 90 degrees, right? So here is 90, now 180, 270, 360, and then 60 more gets me to 420. And I'm just kind of estimating, right? I just need it, I would say I want that red line to be more than halfway between the, in the first quadrant. So like 45 degrees is halfway, 60 is a little bit more than half. But I'm just kind of eyeballing it. Is that cool? So I'm just kind of counting in my head by 90. Okay. Anybody else? We can do some more. We can talk about some more stuff if you're interested, or if you feel like you're missing stuff still. Anthony? You're okay? Okay. So you guys know what's coming by now. If you guys want to take out your calculator or pencil and put everything else away.
Want to, not really. Have to.
Don't even act surprised. Jordan, how are you? Give you a chance to ask some questions.
Like another day or later.
Yeah, like another day. Any day. Other than